welcome Arbel Harpak. He's going to talk about a litmus test for confounding in polygenic scores. The mic is first.
Everyone, good morning. My name is Arbel Harpak. Can you hear me well? Yeah, great. It's an honor to be here. Today we'll talk about what's actually baked in polygenic scores. So as has been mentioned today, polygenic scores are genetic predictors of complex or polygenic traits. And in their simplest forms, polygenic scores are just sums over alleles carried by individuals in the blue XIs here, multiplied by the effect of each allele on the trait in question, as estimated in a GWAS for the trait. And once we have this function estimated, we can use it to predict to plug in the genotype of a previously unobserved individual to predict their trait value. And polygenic scores have intended applications in many fields, starting from clinical risk prediction, but also in basic science, including genetics, evolution, even social sciences, and recently in embryo selection. And the applications just get more and more controversial from here. And I want to posit today that underlying really all of these applications is this premise that polygenic scores capture real direct genetic effects of one's genotype on their phenotype. But research in the last few years has shown that that's not always the case. Namely, there are factors other than direct genetic effects that are captured in polygenic scores. And primarily, I'm talking about stratification, population structure confounding, where we have some population structure in our GWAS sample, and that structure is correlated with the trait. And therefore, all the genotypes that tag those axes of ancestry will also have spurious correlations with the trait. So we and others, including Mashal here, have shown a few years ago that even in what was one of the largest GWAS until pretty recently from the giant consortium for the trait that we thought, the complex trait that we thought that we had the best handle on, human height, actually suffered from residual population structure confounding. Now, while the specific issues that we saw with giant may or may not extend to modern day biobank scale GWAS, I think it's fair to say that the problem is still unquantified, and it's a problem of a magnitude that is largely unknown. So just like stratification, we also have other factors that are culturally or socially confounded or mediated, such as assortative mating and dynastic or indirect parental genetic effects that can be absorbed in GWAS estimates and polygenic scores in turn. And I'm going to refer to this three factors by the acronym that they naturally spell out, which is SAD effects. And what I want to point out is that the SAD effects here are not plotted to scale. And this is not purely due to my poor PowerPoint skills, but actually to the fact that we don't know what the magnitude is. Namely, we don't know what the relative contribution of direct versus non-direct factors to polygenic scores. And this should, of course, impact our application and interpretation of polygenic scores. So this motivated us to develop a method that decomposes the polygenic scores or the variance in polygenic scores with respect to a target sample that we want to apply it to into this different types of effects, but also in terms of population structure, axis of population structure in the target sample. So the main tool that we're going to use to do that is family studies, namely C-based GWAS. And I won't have time to go into the math here. I'll just say that it turns out that doing genetics in families is useful. Namely, let's write down this generative model for how we get, effect estimates in a sib-GWAS as just the sum of the direct effect plus some estimation noise. And this is in contrast to how I would write down the generative model for how we get GWAS effect estimates, which is a sum of the direct effect, the SAD effect, and standard GWAS estimation noise. And writing the two generative model in this way for the two study designs allows us to break down the variance into this direct variance, SAD variance, direct SAD covariance, and noise variance terms. But I also promised that we're going to break this down into axis of population structure, and a natural way to describe population structure in a sample, in the target sample in this case, is principal component analysis, or PCA. So here, for example, I'm showing just a European subset of the 1,000 genomes data, where the first PC kind of maps to Finn versus non-Finn ancestry. The second PC tags mostly northern to southern ancestry in Europe. But what we're going to do is kind of flip our view in a useful way, which is, instead of thinking about individual projections in PC space, we're going to think about how the effect project there. And again, skipping over math, that's going to let us have orthogonal variance components of the polygenic score in a given target sample of direct variance, SAD variance, direct SAD covariance for each PC. And again, these are orthogonal components. So what I'm going to show you here is actually what this decomposition looks like for this giant polygenic score for height with respect to this 1,000 genomes European subset target sample. And plotting the top PCs here on the x-axis, we can see that everything here is kind of boring, but this pops out. This is a huge SAD variance component on PC2, which is exactly the PC that tags the north to south ancestry axis in this target sample. And this is indeed the axis where we already suspected stratification and had good evidence for in this sample, but this lets us put a number on it, and the number is huge in this case. And furthermore, this serves as a positive control in thinking about this method as a litmus test or a diagnosis tool for confounding. Okay, so this is of course not just a problem of the past. We also apply this to modern data from the UK Biobank, and we have some preliminary results with significant SAD variance along PC for many polygenic scores. I want to also briefly mention other types of signals that we can look at. One of them is sort of an inflated direct variance component on a specific PC, which we can actually interpret as evidence for natural selection. I'll be happy to talk about all of this later offline. And the last one that I'll just mention is what I'll call isotropic inflation or isotropic sadness, which is not specific to a PC, but is actually just reflects how much bigger the effect in standard-GWAS are compared to the spec based on a direct variance alone. And we see evidence for that in a bunch of traits. Some of them are perhaps the usual suspects of behavioral and social traits where we see such isotropic sadness, but we also see this in a bunch of physiological traits. So I want to end with some evidence that came about in psychology while we were developing this method, that it's okay for people to be sad sometimes. This is also backed up by seminal work from Pixar Studios. And you may wonder if that is also true for polygenic scores, if that's also okay for polygenic scores to be sad sometimes. Or in other words, you know, if the polygenic score is predictive, should we really care where the associations are coming from? And I want to posit that, at least in my opinion, the answer is always yes. And for all of the applications that I mentioned early on, and whatever applications people will come up with, it is very important to know whether the association that we get at the polygenic score is largely predicting socially and environmentally mediated or confounded effects. And that should often, you know, red light, green light, or at least yellow light our application of the polygenic score to a specific target sample. And I think this also bears a lot of relevance for the issue of portability of polygenic scores, again, because this is with respect to specific target samples. So with that, I want to acknowledge all of the people that led this work. Sam Smith, who's in my lab, who's currently leading the work. as well as Doc, Graham, Dandan, Jeremy, and Khamanesh. Thank you.
So sadly, we don't have time for questions, but we can find Arbel in the coffee breaks or in the poster sessions if you want to. Thank you, Arbel.